In the last section, we did look at the position vector and the displacement vector of an object moving along a plane. When we say that an object is moving along a plane, a typical example is a car going over a hill, or a car going down a valley, or maybe a projectile motion such as this pen. It moves in a parabolic path, which means it has a vertical component and a horizontal component. This is a very good example of an object moving in 2 dimensions. So we're going to extend what we did study last section into answering one important question. How do we define the average acceleration of a particle moving in 2 dimensions? Now, the average acceleration of a particle moving in 2 dimensions is simply defined as the change in the position of that object in a given time interval. Recall that the change in position in a particular direction defines what we call the displacement. So in short, we can define the average acceleration of an object simply as the displacement of a system or particle divided by the time taken. So the average acceleration, the average velocity V average is defined as the change in the position divided by the time interval. It's just the change in displacement divided by the time interval. But what do we know? We know that delta R, it's gonna be delta xi plus delta yj plus delta zk. This would mean that V average will be equal to delta x divided by delta ti plus delta y divided by delta tj plus delta z divided by delta tk. What is this? This is the average acceleration along the x direction. This is the average acceleration along the y direction. And this is the average acceleration along the z direction. So we can essentially conclude that V average along the x direction is equal to delta x divided by delta t. V average along the y direction is equal to delta y divided by delta t. And V average along the z direction is equal to delta z divided by delta t. So the beauty of this process is that we can actually break down a vector such as the average velocity into the velocity in the x direction, which is a scalar, a velocity in the y direction, which is a scalar, and the velocity in the z direction, which is essentially a scalar. When you add the I, the j, and the k, then it becomes a vector. So we can represent the average velocity of this moving particle as V average equal to Vxi plus Vyj plus Vzk. Now, this begs us to define a new term called the average speed. The average speed is just the magnitude of the average velocity, which is going to be equal to the square root of Vx squared plus Vy squared plus Vz squared. This defines the average speed. the average speed of this particular moving particle. Now, because average velocity is a vector, how do we define the direction of average velocity? If you look at this definition, you will notice that delta t is always greater than 0 and by itself is a scalar. By this I mean it's just a number. So the direction of v, which is the average velocity, is the direction of the displacement. Let me say that again. The direction of the average velocity is simply the direction of displacement. Because the change in time is basically a number, what this means is that the average velocity of a particle and the displacement of the particle depends only on the initial and the final point. Let me say that again. The average velocity of a particle and the displacement of a particle only depends on the initial and the final point. It really doesn't matter the path it takes. Let me illustrate what I mean by this. Let's say that the particle moves. We have a square. This is point A to point B. Now, if you are to move from A to B, you have three choices. You can either go through 1, you can go through 2, or you can go through 3. I can even add a fourth choice. You can go through 4. You see, irrespective of the path that you will take, the initial, which is point A, and the final, which is point B, remains the same. You see that 1 is the shortest and 4 is the longest. So the distance between A and B is shortest in 1 and longest in 4. So this is a very good example that explains the difference between distance and displacement. Distance is the length of path covered between the initial and the final point, and it actually depends on the path that you take. On the other hand, displacement as well as average velocity is simply let me say that again, sorry about that. Now, the distance between 2 points depends on the path you take. I've demonstrated that here. 1 is the shortest, which is a straight line between A and B, and 4 is the longest because it's windy. 2 and 3 are equal. But the displacement between 2 points, as well as the average velocity, does not depend on the path you take, but simply depends on the initial point and the final point. What this means is that at all times, the displacement of a particle should only or can only be less than or equal to the distance between the 2 points. It's important you keep that in mind. And before we go, distance is measured in meters, time is measured in seconds. That means that the unit of average velocity is meters per second. Is meters per second.